Hello. Hello. Yeah, this is my first live streaming. So in this live streaming, I wanted to talk about this application, uh, this diagram. So I'll show you this article here, and so this is an article we have mentioned before that this article shows how to use XDP, eBPF XDP to do DNS service augmentation, right? So I talked about the DNS response rate limit with eBPF XDP. So today I wanted to talk more about this with more advanced feature. So one of the feature is about the DNS cookie. Yeah, so I wanted to talk about this series of article is that see if we can learn eBPF XDP technology by exploring this DNS topic, including the DNS cookie and the DNS rate limit. Okay, so again, this is a diagram. So I'll briefly explain how this works. So when you have a UDP DNS UDP packet come into the link layer, and then the IPv4, IPv6. So basically, this is the XDP. This is XDP program going to do in this part of in this section. So it will parse the UDP packet and also verify the server cookies. So when a legitimate DNS client send a DNS request to query to DNS server, the DNS server will create a server cookie and send it back to the client. So next time when the same client send a DNS query to the DNS server, it will have a server cookie. So if the server cookie is fake or is invalid, or there is no cookie in the DNS query, the packet will the XDP program will direct to the rate limiting function. Okay, so two part of a function, verify server cookie and rate limiting. If the server cookie is valid, it will bypass the rate limiting and then to the kernel space IP layer, UDP layer, and then to the DNS application, DNS server. So yeah, that's basically how it works. And now I can show you the code. So this is the original code from the article from the GitHub. And so this is I will use IPv4 packet as example here. So this is where it started to if this is an IP packet, parse the IPv4 header, and if it's a UDP packet, then parse the UDP header, and then if the destination port is DNS port, parse the DNS header. Okay, so if it's invalid, just pass the packet to the application layer, pass to the Linux stack, and then up to the application. And so here is the logic from the diagram. And so if there is no DNS cookie in the DNS query, we will do the rate limit with a BPF tail call. So yeah, later we will talk more about the tail call. And yeah, so if there is DNS cookie in the DNS query, we will do another BPF tail call to do a cookie verification. Okay, so we will learn BPF tail call from these examples. And so let's look at the BPF tail call briefly. So this is BPF tail call is to call the DNS rate limit. So we can go up here, and so this single C program, kernel BPF C program has multiple BPF code section. So we use this sec to separate the different XDP feature to process a packet. So let's find the rate limit. So this is the XDP rate limit for IPv4 packet. This is where the BPF tail call will call, and then see here it's do the rate limit. Okay, so this is the function. This is the function name for the rate limit. And back to the tail call here. Back to the tail call here. Do the rate limit. So first you needed to populate the BPF tail call table. It's a eBPF map with a program array type, and then you needed to populate it to map this is the index of the IPv4 rate limit XDP program, and then we will call into this jump table with this index, and then it will execute this XDP program for the rate limit. Okay, yeah, probably I should draw a call path to make it easier next time. So that's the BPF tail call. Now let's talk about the problem though. I mean, not problem. So in this original program repo, and it has a user space loader, eBPF loader program to load the XDP program, and this is where it you can see here it's open the XDP eBPF program object file, and load the XDP program, load the object file into the kernel, and then here it is to find the eBPF tail call table program array map name here, the jump table, and then update the map with each XDP program. So this is like in the user space. We needed to populate the tail call program array map with each XDP program respectively, and with its index, right? So it sounds kind of so yeah. And so what I have done to this, so I think this part can be like, you know, you needed to populate the call graph, the tail call program array map, but I rewrite the program with the static array map, static program array map initialization. So here's what I did in my code. So I used the eBPF bootstrap project to rewrite this program, and so this is what I did. Instead of using a user space BPF loader to populate the jump table program array map. So this is a program BPF map type program array type for the BPF eBPF tail call. So instead, in the eBPF kernel code, I statically initialize the tables with the XDP program indexed by this number. Okay, so and yeah, so this is I used the two tail call program array map. So that's for cookie. Another one is for rate limit. So this is the rate limit, and so this is the index number, and in the table, this is the actual function. Okay. So in the main XDP program, so this is the main entry of the XDP program that will attach to an interface. And so once it attaches to the interface, and it will when the code runs here, it will use the BPF tail call to with this index that has the value of rate limit IPv6 XDP program to call that program. Okay, yeah, I think I'm not really good at using this browser-based mouse to click around. Maybe I should use the just use the terminal to explain this, and draw the, and basically just map the code with this diagram. Yeah. Okay, so this is just a experiment. So for live streaming, hope I know it's kind of confusing the first time. Yeah. Let's end it here.